So, we are discussing training artificial neural networks. So far we have discussed about how to train a neural net. It is basically based on the concept of learning. There are different learning techniques, and we have considered the learning techniques again varies from different network architecture to different network architecture. In the last lectures we have discussed about how a single layer feed forward neural network can be trained. Today we are going to discuss the multi-layer feed forward neural network training, and then the recurrent neural network training will be discussed. Now, so multi-layer feed forward neural network training basically the similar approach to that of the single layer, but it follows more more what is called the meticulous method. Particularly it is if we consider the supervised training, then it consider algorithms to train it, and the popular algorithm in this regard is called back propagation algorithm. So, today we will discuss about the algorithm as a whole. Now, before going to discuss about training the multi-layer feed forward neural network, for the simplicity of the discussion, we will consider a multi-layer feed forward neural network with the configuration LMN, that is called the LMN network, and it is basically a 3-layer feed forward neural network, and L basically the number of neurons in the first layer, and M denotes the number of neurons in the hidden layer, and N is the number of neurons in the output layer. Or in other words, LMN network is basically a network with L number of input and N number of output. Now, let us see this figure, because our many discussions subsequently will be referred from this figure only. In this figure we have depicted the architecture of a LMN feed forward neural network, and in this architecture, as we see, this basically the input layer, and this is the hidden layer, and this is the output layer. So, the input layer network is called the N1, the network which is there in hidden layer is called the N2, and hidden layer that is there in output is called the N3. So, we can see it is basically the cascading of 3 network N1, N2 and N3 one by one. It is a cascading in the sense that so this is the input to the input layer, and here we can consider L number of inputs. The L number of inputs are denoted as I1, I2 dot IL, and then subscript denotes that it is an input layer. So, these are the input basically, and so the set of input we can denote it is I, and these are the perceptrons in this input layer. L number of perceptrons are there. So, they are termed as 1 1 1 I 1 L like this one. So, 1 indicates that it is the first layer, and then next symbol increases that which the next symbol, if it is I, indicates that is ith perceptron in the first layer. Now, the input to any perceptron is basically this one. For example, to this perceptron input is I1, to this perceptron input is this one, and so on. Now, output of a perceptron in the input layer we denotes it is OI. OI denotes the output of the input layer, and here we can say that the output of the input layer is basically input to the hidden layer. So, input to the hidden layer we denote as IH. Similarly, the output of the hidden layer we denote as OH. So, these are the output of the hidden layer, and the output of the hidden layer is basically output of the output layer, input of the output layer we denote as IO. So, these are the basically input of the output layer, and finally, this is the output layer is called the O. So, here basically I and then O, input and output through this network right. It basically mapped from an input to output. So, this is the idea about it. Now, so this is the working of the multi-layer feed forward neural network, more specifically LMN network. Now, here we will consider few more things. As I told you, this is the network N and size of the network N is L. Similarly, this is the network N2, size of the network is M, and this is the network N3, size of the network is N. So, LMN like. Now, in each perceptron, here in the input layer, they will follow each perceptron, they will follow transfer function and then thresholding value. For the simplicity, okay, so this is the idea. So, if this contains the first perceptron in the input layer, we denote the transfer function as Fi I. So, Fi, this is Fi means the transfer function of the ith perceptron in the input layer, this one. So, this is basically it basically I and theta I, where theta I is the threshold value for this perceptron. So, what I want to say is that, so each neurons are characterized with their own transfer function and then thresholding value, and then input when give it when fed it to this input, it will produce output. Now, this output then will be fed to all the neurons in the hidden layer. So, this output go to this layer, this perceptron and this perceptron and this on. Now, whenever this output of the input layer goes as an input to the hidden layer, they will be associated with weights. So, from the perceptron 1 in the input layer, if it goes to the perceptron 1 in the hidden layer, we can say that it is weighted by V11. So, similarly, we denote Vij, that means it is the weight for the input when it passes from the ith perceptron in the input layer to the jth perceptron in the hidden layer. So, Vij. So, this basically constitutes the weights for all signals that can be fed to the hidden layer, and we can represent this weight by means of a matrix, V matrix, that we have already discussed, and it is similar that of the single layer feed forward network. So, in this case the matrix is size L cross M. So, this is basically LM matrix, L number of rows and M number of columns are there. Next, the output of the hidden layer goes as an input to each perceptron in the output layer. For example, if jth new perceptron it is there in hidden layer, so output from this perceptron goes there and goes all the perceptrons in the output layer. Now, likewise the input to the hidden layer, here also all input to the output layer will be associated with weights. So, these are the weight matrix, and this weight matrix is denoted by Wm, and in this case the size of the weight matrix is M cross N, because from M number of perceptron it goes to the N number of perceptron in the output layer. So, M cross N. So, it is a similar the V matrix that we have discussed in the previous in between input to hidden layer. Here also W matrix is between hidden layer to output layer. Now, again for each perceptron in hidden layer, it will be characterized with transfer function and then thresholding value. So, if it is in the jth layer, jth perceptron in this layer, then we can represent that Fjm, and this basically the input to the jth perceptron, and this alpha is a threshold value. We can assume here that all the transfer function that it basically here for each perceptron is denoted by this one. It is basically log sigmoid transfer function, and in this case we have considered a linear transfer function. That means it will simply the pass input to the output. So, these are the two transfer functions and threshold values are there in input layer and then output layer. Now, similarly, the transfer function that we have considered here for any kth perceptron in this layer is denoted by this one, and here we have considered the log sigma, the tan sigmoid transfer function. So, for the sake of varieties, we have considered different transfer functions in the different perceptrons with the different threshold values in each layer. So, this completes the description of the element network as a multi-layer feed forward neural network. So, now once this architecture is clear, then we will be able to see how this network architecture can be trained. So, train means there are many things are to be learned. So, for training is concerned, the first of all, how many numbers of perceptrons should be there in the input layer. Okay, that obviously specified by the number of inputs, of course. Similarly, number of perceptrons in the output layer, it is also decided by the output. So, these two things are very simple, right? It is easy to do, but so far the learning is concerned, how many neurons are there should be in the hidden layer, it also needs to be learned. So, this m value needs to be learned. So, this is another learning parameter, and then we have considered the threshold values in each perceptron in the input layer. So, these values also needs to be learned. Then alpha j value for each perceptron also needs to be learned, and then here also alpha values for each perceptron to be learned. So, these are the learning parameter therefore. So, m to be learned, theta I values for each perceptron, alpha j values for each perceptron, alpha k values for each perceptron are to be learned. Another also the things to be learned that we have considered here in our discussion, that this is the transfer function, but it can be other transfer function always as well. So, there are many transfer function. So, it is also needs to be learned which transfer function will be better so far the accurate output is concerned. So, all the transfer function that we have discussed, assume that these are transfer function, but here also system should learn what are the transfer function that it should be here. So, these are the different things to be learned. So, these are the objective of learning. So, learning means we have, okay, fine. I also forgot to mention one thing, another learning parameter is V and W. So, these are the most important metrics or parameters to be learned, V, W. Now, in this discussion, it is not possible to discuss all the learning parameters, but they can be learned in the same way any one other parameter can be learned, and for the simplicity in our discussion, we will consider only how this network architecture should be trained so that it can learn the V matrix and W matrix for the application. So, we will learn about how the network can be trained so that this network can learn V matrix and W matrix, and following the same approach we can learn other network parameters. So, this is the objective of the learning that we are going to discuss now. Okay, fine, and for the sake of discussion we will consider these are notation that we will follow, so that we can understand the things completely. We can say any neuron in the input layer as the ith neuron, I is 1 to L. Similarly, any neuron in the hidden layer we denote it as jth neuron, and any neuron in the output layer we denote it as kth neuron. And similarly, there is a weight associated from ith neuron in the input layer to the jth neuron in the hidden layer, we denote it by a V matrix, and the V matrix is like this. So, this is the usual V matrix that we have already used it in the single layer feed forward neural network training. So, it is basically V I j denotes the weights from the ith neuron to the ith neuron in the output layer to the jth neuron in the hidden layer, and their values of I will vary from 1 to L and values of j will vary from m to m, and this way it is an L cross m matrix. Now, so this is the matrix, basically we have to learn it by means of training. We should learn the different elements here in this matrix. Now, likewise we denote the W j k representing, it is the weight from the jth neuron to the jth neuron in the hidden layer to the kth neuron in the output layer. Now, all the weights that is there in this network can be represented by a matrix, this is called the W matrix, and W j k represents basically weight from the jth neuron to the kth neuron, and it is therefore a matrix of m cross n size, where m is the number of neuron in the hidden layer and n is the number of neuron in the output layer. So, this matrix W also needs to be learned, and by means of training process we have to learn this matrix. Now, so far the training is concerned, basically training here in the neural architecture needs a number of computation. We can systemize the computation in the 3 steps method. First we have to compute the input layer, then hidden layer and output layer. So, we say that input layer computation, hidden layer computation and output layer computation. Now, so far in our computation is concerned, computation is based on some training set. So, here we denote the training set as T, and T, the training set consists of the input data and then output data. For any input I which is belongs to T I has an associated O I O. So, it is basically I and O one sets. This sets is basically supervised training sets. So, T is the training data here. So, given the training data, right, we have to learn the different network parameter, in this case V and W matrix. Now, to learn it, or as a process of learning, we have to compute the different layers in the network. And so, now let us see first the input layer computation. Now, the input layer computation can be discussed like this. Say suppose any input I which is in T I we have discussed about, this is the input set, and this A I consists of L number of input for each neuron to the input layer. So, we can denote at I 1, I 2 1, I 2 this one. Okay. So, this basically is a one input that is there in the input set. So, this is basically the one input which is belongs to this training set T I, and the output layer combination is trivial in this case. This is because whatever because we have considered the linear transformation. So, linear transformation means y equals to x. So, the whatever the value of x will be directly passed to the y. So, in this is why the output layer combination is that if O I is basically the output instance at any time, then its input is I 1, or in other words, if I 1, that means if this is the input, then its output is also O I, but same, because of linear transformation. Now, all these things we can represent in terms of a matrix. So, all these, right, it can be represented in a matrix like I 1, I 2, I and so on. So, this is basically the matrix, and as this is a L number of inputs data are there. So, this is basically L cross N matrix. Similarly, I 1 also L cross N matrix. So, what we can say that, so this is the input layer combination, that means input to any perceptron in the input layer will be the output of that perceptron in that layer, and this the any neurons input and corresponding output can be represented by means of this matrix formulation. This matrix of size L cross N, L cross 1, and this matrix of size L cross 1. So, this is the idea about the input layer computation, and similarly we can say that if this is the output of a perceptron in the input layer, then that will work as a input to the hidden layer. Now, if we consider any jth neuron in the hidden layer, then its input can be considered as IJH. Now, this IJH can be expressed by this of product. So, basically it is from the first neuron to the jth, this is the weight, the matrix, what is called the weight values, and then it basically the output of the first neuron in the input layer. Similarly, the second neuron to the jth, and then output from the second neuron in the input layer, and this is the Vij, the weight from the ith to jth, and it is basically the output of the jth neuron in the input layer. So, this concept is there, and this basically is a summation of all the inputs with their weights, it gives the input to any perceptron in the hidden layer. So, ijh is basically input to the jth perceptron in the hidden layer, and this basically the calculation of our input to the hidden layer. Okay. And now this expression can be represented in the matrix form, which is represented here. Here if basically IH is basically all the inputs to the hidden layer, it can be represented as V transpose matrix and OI matrix. So, OI basically output of the input layer, and V transpose matrix is a V matrix and it transpose form. So, in other words, if IH is basically M cross 1 matrix and VTH is a transpose, V is a L cross M and it transpose become M cross L matrix, and OI1 is a L cross matrix. So, whole the things or whole this input layer computation can be expressed in the form of a matrix representation. And what we are observing is that all the calculation, for example, input to the input layer or output of the input layer and input to the hidden layer is basically input layer calculation, and all these computation can be expressed in the form of a matrix as it is here. So, this is basically matrix representation and then matrix operation, and then neural network training and then it is describing the model is nothing but a matrix model or matrix formulation of the model. So, this gives the input layer combination, and then we will come to the hidden layer combination. Now, we know exactly what is the input to any perceptron, any jth perceptron in the hidden layer. Now, our task is to calculate what is the output of the jth neuron in the hidden layer. We represent the output of jth neuron hidden layer as this form OGH, and as we have discussed that the transfer function that it used is basically log sigmoid, and it has this form, and these are the alpha h indicates that it is basically it is alpha j, better we can write that it is basically the threshold value of the jth neuron in the hidden layer, and ijh if it is the input. So, it is basically e to the minus alpha I concept. So, it is the output. So, this output is basically for the jth neuron in the hidden layer. Now, the way we have expressed the matrix representation. So, this calculation or the output combination also can be represented in the form of a matrix, and the matrix will look like this. It is basically that matrix we can say that OH matrix. This is the OH matrix. This means the output of the hidden layer, and output of the hidden layer, because m number of perceptrons are there. So, it is a matrix of size m cross n. So, it basically includes the output for the first perceptron, second perceptron, and this is the mth perceptron. So, it basically matrix. That means, all the outputs of the perceptrons in the hidden layer can be represented by this type of matrix. So, this is another matrix to compute the hidden layer. Now, so the hidden layer output is known, hidden layer input is known, input layer input is known, input layer output is also known. Now, we are in a position to discuss about output layer computation. Now, in case of output layer, we know output of the hidden layer works as an input to the output layer. Now, if there is any neutron, say kth neutron, and we denote the IKO represents that it is basically input to the kth neuron at the output layer. So, is a input to the kth neuron at the output layer. Now, this input is basically is a summation, is a sum of the products of the weight matrix corresponding to the output from all the perceptrons from the hidden layer. So, this can be expressed, this is basically output from the first layer in the hidden layer, output from the second perceptron in the hidden layer, and output from the mth perceptron in the hidden layer, and is multiplied by this product is the weight matrix, weight values from the first neuron to the kth neuron, from the second neuron in the hidden layer to the kth neuron in the output layer, and so on so on. So, this way this basically is an expression is the input to the kth neuron at the output layer, and there are n number of neurons. So, k will varies from 1 to n. So, this basically computes the input to the output layer. Now, this expression can be expressed in terms of matrix representation, which is here. So, I/O denotes all the inputs at the output layer, and this can be expressed the transposition of weight matrix and multiplied by the OH. O is basically output of the hidden layer. This output of the hidden layer we have already learned how to get it. So, this way the matrix representation of the output layer, input to the output layer can be obtained, and we can represent this matrix as this is a n cross 1 matrix, this is n cross m, because W is a m cross n matrix and this is an m cross 1 matrix. So, this basically the input computation at the output layer, or is called the output layer computation. Now, we will discuss about the output of the output layer. Now, similarly the way the output of the input layer hidden layer we have calculated, in the same way we can express the output of the output layer. Now, we can see that we have already mentioned that the transfer function that we have used there in output layer is basically a tan sigmoid transfer function, which takes this form. So, it basically the output of any kth neuron in the output layer. So, this is the output of any kth neuron in the output layer, and there are n number of neuron in the output layer. So, k values varies from 1 to n. Now, so this expression is for a particular perceptron. Now, as a whole for the entire network at the output side also can be expressed, and that too can be expressed using the matrix representation. So, this is the matrix representation for the output layer. Here O denotes the all outputs that can be obtained from the output layer, and this basically this is the entry of the output of the first neuron in the output layer, and this is the second neuron in the output layer, and this is the nth neuron in the output layer. So, these things also can be represented by means of a matrix, and here alpha O is denotes that what is the threshold values. Now, here if we can for the simplicity we can consider that only one values of alpha. So, alpha I is basically the threshold values in the input layer for all the perceptron. For the simplicity we assume it. Similarly, alpha H we denote the threshold values of all perceptrons in the hidden layer, and alpha O denotes the threshold values of all perceptrons in the output layer. Now, this is just simply an assumption that we consider same values of threshold values for all neurons belongs to a particular layer, but in actual practice it is not necessarily the same. We can consider the different threshold values for different perceptrons in the network, but it will increase the complexity, it will demand more calculations. So, otherwise it is not the issue, it is only the issue of computation time. Now, we have discussed about the different layer computation, and all these layer computations will be used to train the network, because this is the is a mathematical manipulation that how we can represent a neural network mathematically. Now, we have just now discussed that how the entire neural network can be represented mathematically, and that mathematical representation in the form of a matrix representation. Now, in the next lecture we will discuss about using these are the different calculation how we can train the network. Now, for the training a multi-layer feed-forward neural network, there are many training procedure, but in this lecture we will discuss about a particular which is most popular, the back propagation algorithm. So, that will be discussed in the next lecture slides. Thank you.